Hello, this is going to be Lock Design Video 3. In this video, we're going to look at stopping power analysis attacks and timing attacks in electronics, specifically electronic locks. To recap, in Lock Design Video 2, we discussed what is a pick-proof lock, what makes a lock secure, and how we can prevent feedback to attackers in mechanical locks. We found we could not compress information and needed a unique space for each possible combination. So a 5-pin lock with 5 possible cuts could have 5 times 5 or 25 feedback group positions and not 5 to the 5th power or 3,125 possible combinations. So there's still 3,125 unique keys. However, if an attacker were able to perfectly interpret the feedback from the lock, they would still need to try, in theory, up to 25 possible positions to open the lock. So those would be the feedback-proof ones. There's a myth that only electronic locks can be made pick-proof because they do not provide any feedback. And this is false for 2 reasons. One, as we saw in video 2, we can prevent feedback in mechanical locks. It's not ideal in the way we do it. It's not super efficient, but it is possible. And 2, electronics can still provide feedback if not properly implemented. So there's things called side channel attacks which exploit the implementation of an algorithm or function rather than a flaw in the function itself. And 2 examples are timing attacks, which are attacks based on measuring how much time various computations, such as comparing an attacker's given password with the victim's unknown one, take to perform, and power monitoring attacks, which are attacks that make use of varying power consumption by the hardware during computation. And I got those definitions from Wikipedia. So attackers can do things such as monitor the time it takes a system to compare 2 passwords or how much power is consumed when comparing 2 passwords to evaluate whether or not the password they're trying is closer or further from the true password. And that's because even though in theory equating 2 values, the 2 values would be sort of equally compared without providing any adjustment on feedback. In reality, when the computer is actually comparing the 2 values, it has a set of transistors which are making up AND gates and OR gates, which are sequentially doing the logic to compare whether or not the 2 values match. And they will require different amounts of power depending on whether those sequences match at the beginning or end. And they will take different amounts of time to propagate the signals. And that's what attackers can look at to try to get feedback in a similar way to a safecracker looking at, say, how much the dial rotates with each new password or combination. So what we can do is we can take the rules from video 2 for mechanical systems and sort of abstract them to apply to both mechanical and electrical systems. And when we do that, we come up with the following rule. When checking if a provided value matches a single predefined valid value in a domain, to prevent information leakage about the predefined value to attackers, the system must maintain unique data for every value in the domain, where each datum contains the validity of only one value. So that's essentially saying what we said for a mechanical system, but we've abstracted it some so it can also cover an electrical system. And just like in a mechanical system, we need to continuously harden the lock for other things. We can't make the lock out of glass where they can see the pin tumblers. You also need to prevent bypass methods and prevent access to the unique data in the electrical system or the memory. So you wouldn't want a lock that's completely see-through. The attacker could identify the correct value in advance. The same way you want to protect your memory and other bypass methods on a computer. If the unique datum for every value reminds you of a one-time pad, that's because we're making a form of one, and I'll show you that here. So here's an example of performing the rule we just saw a second ago as a one-time pad. So on the left, we have a user-provided value for our domain that can go from 0 to 9. What we don't want to do is take those values and use their binary value and use those to do any computations. What we want to do is assign a unique plain text value for them that only uses a single bit. And then we can, if we were doing this as a one-time pad, XOR that with our key and get the resulting ciphertext. And in the case of a lock, the ciphertext where all the bits are the same would be one where the correct password or plain text was provided. And that could be, you could reverse it so it's ones and zeros and the ciphertext is all ones. The 1 versus 0 is, it doesn't matter. But that's just showing an example of what this looks like as a one-time pad. This isn't the ideal way to do it, and what the advantage of this is that we're only comparing one value at a time. So there is no series of gates or transistors. There's no series of AND gates to analyze the timing on. It's always going to compare one value, and I'll show you that in this next slide. So, well, actually, I'll go back one. It won't let me go back, so I'll show you on this slide. So what we're doing in this slide is, this is an example in C, and we're creating an array, and we're using some macros to set bits and check individual bits. So we have an array of an integer type, so 4 bytes with 32 bits in it. And we're setting the 7th bit as true. And then what we're doing is we're getting a value, a user-provided value from the user, and we're going to use that as the index to check. So the user provides us a number, 0 to 9, and we then check, is bit 0 or bit 9 valid? And in doing this, we do the exact same operation. There's no more or less gates whether or not the person chooses a value that's closer to our unique key or not. So if they choose 6 or if they choose 0, the amount of time and power it takes to compute this will be the same. So this, if you were implementing this example in C, the memory isn't protected here or encrypted in any way, and if an attacker had access to the computer or microcontroller, they could attempt to read the unique data from memory. So for this particular example in C, you would want to protect the microcontroller in some way such that the attacker could only provide the user-provided value. So that would be, in essence, you would put the microcontroller inside the lock or inside the safe, and you would only have the 2 wires going out for the keypad, or however many wires you have for your I don't know, serial data or whatever you're doing for your keypad. So, inherent flaws, a weakness of all locks. So, what does it mean to lock something? It means, one definition I think that was useful is to restrict access to the full functionality or data, a computer, mobile phone, file, etc., especially by requiring a user to verify their identity with a passcode or other form of authentication. That's from Oxford Languages, which I guess Google uses. So in order to verify, the lock needs to know the key and ciphertext. They need to know what's correct and have a method for interpreting what the user provides. So the exact verbiage can shift, the analogy, you can shift it around, but if we're thinking of it as a one-time pad, the lock needs to know 2 of the 3 components of a one-time pad. A one-time pad is composed of plaintext, key, and ciphertext, and it requires that the attacker does not have access to the key or plaintext to decode the ciphertext. The inherent security, a part of the inherent security of a one-time pad is that the attacker only has access to the ciphertext. But because we want a lock to verify, we want the lock to decide whether or not it should grant or deny access to something. It needs more information. And even if the lock is only used once, it does tell the attacker if the provided value is correct. and this reveals information about the key and the plain text. So the attacker could, in theory, decode an n-bit key in n attempts, assuming the attacker is able to properly interpret all feedback. And this, to me, right now, appears to be a fundamental flaw of any lock, mechanical or electronic. And it means we must use other means beyond zero feedback to further restrict attackers, especially when we start talking about computer systems where we can brute force a massive amount of numbers and computations extremely quickly. We need to do other things, like we discussed in video 2, with either with staging or automatic lockouts, lockdown kind of features, or minimum amount of times between attempts, or a minimum amount of interactions or steps the user needs to take before attempts to slow down an attack. And that's it for this episode. In the next episode, I want to talk about combinations and permutations, and what we've learned so far has taught us about them, and also how false gates or false positives affect those numbers. And if you're interested in anything else, let me know in the comments, and we can check it out. All right. Thank you for watching. I hope something in there was of value to you. Also, disclaimer, these are my theories or my hypothesis. If you think I've said something wrong here, or something doesn't seem right to you, please let me know, and yeah, just check me in the comments. Let me know that, hey, I'm not sure if this is right, or I think you're wrong, and we'll figure it out. Okay, well, thank you for watching. Bye.